Before we continue with the exercises, there's a small correction. So exercise 7C. So we showed that alpha norm u minus w square is less than or equal to a of u minus w u minus v plus a of u minus w v minus w for all v in w, and this, since it is in w, this term became 0. So this is less than or equal to m times norm u minus w norm u minus v, and therefore you get that norm of u minus w by cancelling one of them is less than or equal to m by alpha times norm u minus v, and since this is true for all v, I can put infimum v in v here, v in w. Okay, so that is how we do. The error is that I had put a square when I did these last two inequalities. You might have already noticed it. Anyway, if you did not, here's the correction. So please, this is how it should read. Okay. So now we will continue with the exercises. So I think we are now in number 12. So A, H Hilbert space, and S and T belong to L of H. Let lambda not equal to 0 be an eigenvalue of ST with eigenvector T U. Eigenvector U. Show that Tu is an eigenvector of Ts for eigenvalue lambda. Okay, so solution, this is very easy. So you have that S of Tu, St is the vector, so S of Tu is lambda u, and lambda not equal to 0, and obviously u is also not equal to 0, so this implies that Tu cannot be 0. Okay, so Tu is not 0. Now Ts of Tu is T of St of u. St of u is lambda u, is lambda Tu, and Tu is not 0, and therefore Tu eigenvector for Ts corresponding to lambda. Okay, so that is a very trivial statement. So now non-zero eigenvalues of St and Ts are the same, and you have T of the null space of St minus lambda I is equal to the null space of Ts minus lambda. Okay. So solution. So we can, by A, we can also show lambda not equal to 0 eigenvalue of Ts implies lambda eigenvalue of St. Okay, so that's the same thing. In T and S there is nothing sacred about that, so you can just interchange the roles and you can do it. And you have already shown, and by A again, if u is an eigenvalue of St, then T of u is eigenvalue eigenvector of Ts, and therefore we have shown we have the T of n of St minus lambda I is contained in n of Ts minus lambda I. So now we have to show the converse. So let u belong to n of Ts minus lambda I. Okay, so we have TSU equals lambda u. So this implies that u is T of SU by lambda. So it is T of something. So it is enough to show, SU by lambda is an eigenvector of ST. So we just have to show the ST of SU by lambda is equal to S of TS of U is lambda U. So lambda U by lambda gives U again, which is lambda times SU by lambda. Okay, and that completes the proof. Therefore, we have shown that null space of TS minus lambda I is contained in T of the null space of ST minus lambda. Okay, so we have shown that all the non-zero eigenvalues of TS and ST are the same. Okay, so remark 1, nothing can be said about lambda equal to 0 in infinite dimensions. For instance, you take h equals little l2 and you take t of x equals 0, x1, x2 and so on. Okay, so x is x1, x2 and s of x equals x2, x3 and so on. So both of them are bounded linear operators, we have seen this. So if you take E1, then S of E1 is 0. So E1 is an eigenvector for lambda equal to 0. So because this also implies that TS of E1 equal to 0, okay, for TS. On the other hand, if you take S of T, this is the identity map. S of T, you go by 0 and then you push away the 0, implies lambda equal to 0, not an eigenvalue. Okay, so you do not have. Of course, in finite dimensions, we have eigenvalues of ST and TS coincide. We have already shown for lambda not equal, already shown. So if 0 is an eigenvalue of ST, 0 eigenvalue of ST, that means determinant of ST equals determinant S into determinant T equal to 0. This implies TS is also singular because its determinant is also 0, implies lambda equal to 0 eigenvalue of TS. Okay, and therefore in the finite dimensional case, in fact you can show that the characteristic polynomials are in fact the same. Okay, so that you might have done in linear algebra, and so okay. 13, H Hilbert space, okay, A from H cross H to C, okay, such that A of alpha u plus beta v times z equals alpha au z plus beta avz. That is linear in the first variable. And then A of uv equals A of vu bar. And 3, A of uu is greater than or equal to 0. So this for all u, v, z in H and alpha beta in C. Okay, so this is almost looking like an inner product, except that the third condition is a bit weak. It doesn't say that this is a norm. In fact, u equal to 0, AUU equal to 0 may not mean that u equal to 0. So, but even then you have the analog of the Cauchy-Schwarz inequality, namely mod AUV is less than or equal to root of AUU root of AVV. The square root is well defined for all uv in H. So this identical proof as in the Cauchy-Schwarz inequality. So solution, so let me redo it once more. So you have that uv in H, and then take alpha in C such that mod alpha equal to 1, and alpha times AUV equals mod AUV. It's always, you can always do this. Okay, let T belong to R. So you have 0 less than or equal to A of alpha U minus TV, alpha U minus TV by the third property. So that's equal to, so A UU, and then alpha will come and alpha bar will come from the other one, that will give you mod alpha square, which is 1, okay, minus A alpha U, so T times V, T is a real number, then minus A of again T times V alpha U plus T square AVB. Now this is nothing, one is the conjugate of the other by the second property, and therefore this is equal to AUU minus 2T real part of A alpha UV plus T square AVB, which is equal to AUU minus 2T times, now alpha will come out, alpha AUV is mod of it, and the real part is therefore itself, so mod AUV plus T square ABB. And now you again have a quadratic form which is never changes sign. That means the roots of the quadratic should be either coincident or imaginary, and therefore you have that B square is less than 4AC, so 4 times mod AUV square is less than or equal to AUU 4 times plus into ABB. And that's exactly this relationship here. Okay. So for the Cauchy-Schwarz inequality, you don't need the full power of the inner product. Okay. 14. H Hilbert space. A belongs to L of H, self-adjoint. Then sup of AXX norm x equal to 1 equals norm A. So norm A has, you have now one more formula for the norm. Okay. So solution, let M equals sup norm x equal to 1 AXX. Okay. So if norm x is equal to 1, then mod AXX, sorry, sup of mod AXX, excuse me, very important. Okay. Mod of AXX is less than or equal to norm A into norm x square, which is equal to 1, and therefore you have that M is less than or equal to norm A. Now let xy in H be arbitrary. So let us compute A of x plus y equals AXX plus AXY plus AYX plus AYY. Now what is AYX? This is nothing but y A star x equals YAX, which is equal to AXY conjugate, and therefore this is equal to AXX plus 2 real part of AXY plus AYY. Similarly, A of x minus y will be equal to AXX minus 2 real part of AXY plus ayy. So when you subtract, you get 4 times real part of axy is equal to a of x plus y minus a of x minus y. So that if I take, this is therefore less than or equal to mod of this plus mod of this, that is equal to m times norm x plus y square plus norm x minus y square. So let me put 4m and divide by 4, and now we know what this is. This is the parallelogram law. So that's equal to 2m times norm x square plus norm y square. Therefore, so now you take alpha, mod alpha equal to 1, alpha times axy equals mod axy, and use alpha x instead of x above. So if you do that, so you substitute alpha x instead of x, so you get mod axy, okay, is less than or equal to the 4 I am going to divide, so I get m by 2 into norm x square plus norm y square. Okay, now ax not 0 and you set y equals, choose, let ax not equal, if ax is 0 there's nothing for us to do because we are looking at the maximum value so of axx. So ax not equal to 0, so y equals norm x by norm ax into ax. So let us use this y in the above inequality. Then if you take the left hand side, so you get ax give you norm ax square, will cancel with one of them here and norm x will be there. So the left hand side will be norm x times norm ax, okay, is less than or equal to m by 2 times norm x square. And what is norm y square? Norm y square is precisely norm x square again, which is equal to 2, so this is m times norm x square. So if you cancel one norm x, you get norm of ax is less than or equal to m times norm x, implies norm a is less than or equal to m. We already saw that norm a was bigger than or equal to m here, and therefore we have both of them. So this implies that norm a equal to m. Okay, so that proves the thing. 15. H. Hilbert space A in LH self-adjoint. So we already know that the spectrum is contained in the real line. Now we are going to give some more precise information. M equals inf norm x equal to 1 axx. So now there is no modulus, and capital M equals sup axx norm x equal to. Then sigma of A is contained in the closed interval M capital M, and M capital M belong to sigma A. Okay, so this is the, so we have a more precise characterization of the spectrum of a self-adjoint operator. So solution, let lambda be strictly bigger than capital M. Okay, so lambda I minus a x x, okay, so that's equal to lambda times norm x square minus axx. Now axx is less than or equal to m times norm x square, so this is bigger than or equal to lambda minus m norm x square, and this is strictly positive number. Okay, so therefore you get, now if you apply Cauchy-Schwarz on the left hand side, so you will get that lambda minus m times norm x is less than or equal to norm of lambda I minus a x. So this is a familiar thing. We have used this many times in our in the theorems, the famous lemma. So lambda I minus a star is itself lambda I minus a, and this has closed range and 1 1 by this inequality here. Okay. Okay. So therefore you have that lambda I minus a is invertible. Therefore lambda belongs to rho t. Okay. A rho of a. Okay. So similarly, you have, if lambda is less than m, you can do the same kind, less than small m, sorry, you can do the same argument and you will get this imply that lambda belongs, so this belongs to rho of a, so lambda belongs to rho of a again, and therefore this implies that sigma a is contained in small m, capital M. Okay, so now for the remaining thing, so now you consider this bilinear form, or the this form AUV equals mu minus AU v. So if this is equal to m times uv minus AUV is u times a star v, which is AV, a equals a star, okay, and this is equal to mv minus u inner product mv minus av, which is equal to a of vu conjugate. Okay, so we have this, and of course linear in first variable, that's obvious, and finally AUU is m norm u square minus AUU, and of course by definition of m this is greater than or equal to 0. Therefore by exercise 13 we have the Cauchy-Schwarz inequality. So mod of mu minus AU v is less than or equal to mu minus AU u power half and mv minus AV v power half. Okay, so that's the Cauchy-Schwarz inequality, which is less than or equal to norm of mi minus a power half into norm v into mu minus AU u power half. Okay, therefore from this you get that norm of mu minus AU is less than or equal to norm of mi minus a power half into mu minus AU u power half. Okay, so now you choose un in H, norm un equal to 1 and un tending to m. This is the supremum, so you can always find such a sequence. So if you apply that, you get that norm of m un minus aun is less than or equal to norm of mi minus a power half mun minus aun un, and that of course goes to 0 by our choice of this. So if m I minus a were invertible, we have un can be written as mi minus a inverse mun minus aun. So I am just applying a operator and its inverse, so I get back the identity, so that will be equal to un. That means this will imply that un goes to 0, but norm un equal to 1. So we have a contradiction, and therefore this implies that mi minus a not invertible implies capital M belongs to sigma A. So similarly, you can do small m also belongs to sigma A. Okay. So that proves this thing. So remark, combining exercise 13, 14 and 15, we have that if A is in LH self-adjoint, then either norm A or minus norm A belongs to sigma of A. Because one of them, either A will be equal to capital M, norm A will be capital M, or minus norm A will be equal to small m. We don't know how the thing behaves, and therefore one of them definitely has to be the because that is the supremum of the mod AUU. So you will get either small m or capital M when you remove the modulus, and therefore you get one of them has to be in sigma of A. Okay, so we will wind up this chapter and we will take up another topic next time.